during this talk, we're going to talk and explore Falco. In particular, we're going to see what's happening in our system and how Falco traces everything from the kernels upwards to provide us the last line of defense, especially in cloud-native security contexts. I don't know, maybe how familiar you are with Kubernetes, containers, that kind of shit that today we have fun with. But basically, that's the landscape that Falco targets. So hands up who already knows what Falco is here. No one? Okay, I can go away. Bye-bye. Anyway, if you want to know more, you can go on GitHub, Falco Security /Falco. Falco, I will explain soon what Falco is, so maybe you can take a look after the talk to our GitHub. So briefly, before to really start, a bit of history. Falco was created in 2016 by sysdig as an open source project from day one. I don't know why sysdig did it. I don't know why sysdig pays me a salary, but this is life. I mean, and since the beginning, the focus of Falco has been to parse libsysp events. Libsysp events are basically events from this library, libsysp, which is another open source library from sysdig that handles syscalls, proc, file system information, metadata from containers, from orchestrators like Mesosphere, Kubernetes, and things like that. Anyway, the scope of Falco is to track everything happening at the lowest level of your system and match these signals with security policies, and eventually and hopefully fire alerts. 2 years later, 2018, Falco was donated to the CNCF. The Cloud Native Computing Foundation is a branch of the Linux Foundation, and Falco has been the first ever sandbox project in the security topic. It started to gain some really serious traction to the point that me and the other 3 maintainers had to basically start a boring weekly community call, to which, by the way, I invite anyone to participate on Wednesday, 5 p.m. Italian time. So the past January, Falco has been officially incubated by the CNCF branch of the Linux Foundation, and we don't know where we'll end up with this. We'll see. Who am I? My name is Leonardo Di Donato. I'm an open source software engineer at sysdig, where my daily job, as probably you already imagine now, is to code Falco, evolve it, and maintain it. In case you're wondering, yes, I spend all day on GitHub because, I mean, there is the source code. So basically, my workflow is GitHub and kernel. So that's it. Here, there's a photo of me that I use usually in talks when I go in USA, States, and other parts of the world. I imagine I should have removed the caption here about Italian hand gestures because I see that these jokes does not work really well in Italy. So you can usually find me on Twitter, GitHub, usually the webverse with Leodido nickname. Feel free to follow me, send me direct messages, whatever. I like to socialize. We can talk about everything about BPF, kernel, Linux, and security. So the plans for the next 30, 40 minutes are to look at beautiful photos of our country when it does not rain like today. And to get the skin, Falco tries to solve the runtime security problem by, even for cloud-native runtime, cloud-native environments, by basically tracing all the syscalls happening at the kernel level. So this talk is split in 3 parts. First of all, we reason about the runtime security, the concept of runtime security in modern contexts, in cloud-native contexts for which Falco is made for. So then we'll focus on how to secure all these environments by tracing the Linux kernel, why and how to make syscalls coming from the Linux kernel with container metadata, container other information grabbed from container runtime APIs, Kubernetes audit logs, and so on. We'll see how Falco engine then asserts rules as a rule language, a rule engine that is used to assert those rules that define policies against the events that we collected. And finally, we'll try to have some fun about some CVEs on Kubernetes and some other detections that I will demo. So what does security mean to me? how to characterize the security concept. I don't know you, but I personally don't want anything happening in my system without me even noticing it. I want to control things that can happen and things that cannot, at least in this context. And since preemptive control is not always possible, and we know this, I also need deep visibility into my system to be able to know as soon as possible what just happened. Basically, I think of security in terms of two words, prevention and detection. What do two words have in common? Someone wants to reply? Don't think so. Policies. Both concepts use some kind of policies, right? To describe the allowed or disallowed behavior for a process in the Linux context. In terms of system calls, their arguments, and host resources assessed. The difference are that the first word, prevention, is connected to the concept of enforcement. Do not allow some actions from some persons to happen at all because of some policies. Tools in this category usually change the behavior of a process by preventing system calls to even happen, while tools in the other category, the policy concept in the other category is a bit different. The concept there is to define some policies, to monitor the behavior of processes, and be notified when they step outside so that you can take countermeasures then. So we also can think about security in terms of this, I will not say dichotomy, because they are the same face of a medal, but we can also describe security looking at these two aspects in terms of enforcement and not versus auditing. Not versus is important. I will explain now why I think so. Some example anyway of enforcement tools are seccomp, APF, CLinux, AppArmor, even the authorization mechanism like Kubernetes rules-based access control or the policy-based admission plugins that we have in Kubernetes fits this category, since they will prevent something to happen on your cluster depending on some policy. While tools like AuditD and Falco itself belong to the other side, the auditing side of the security topic, a topic that, especially in cloud-native and modern contexts, has not been solved. There's really a lot to do. But now, can Falco solve all our security concerns in these contexts? I have to be honest, not at all. I mean, software is made of layers, like this image shows, and so it's security. And this is even more true in cloud-native environments nowadays. As you can see the scheme here, I drew in the slide, these are environments that embrace change as their constant, as their fundamental part, opening the doors to a lot of possibility, but also to a lot of unknowns. I mean, you have orchestrators that brings down pods with services, brings up others on others nodes, with different maybe also adaptive limit and resources. So it's change. Everything changes here constantly. And the simple rule of the world is that sometimes, like this year, for example, unexpected things, I will not say shitty things, but unexpected things happen. And I mean, what have you ever expected in the pandemic to assist to an in-person conference? I will not ever expect it. So unexpected things happen. And anyway, we have to respond to those events in a timely and accurate way. So Falco is here to enable us to detect intrusions, malicious behaviors, generally security threats at runtime. But let's also be clear about this fact that security is made of layers, and I'm not suggesting to use Falco as a solution for everything. I already told with some people here that were yesterday at dinner about this concept, stressed people about this concept. We need to use prevention tools and detection tools together in a layered fashion. For example, we have to implement what's called a defense in depth strategy. Defense in depth term is a term that derives, since we're in Rome, from a late Roman military strategy that was a bit different from the software concept. That concept was about intentionally setting ground to reorganize and then counterattack the opponents, and because they had not all the strength to govern all the borders, all the attack surface. In computer science, defense in depth means that at every level, every degree, you have to use combined techniques of prevention and techniques of detection, maybe creating a feedback loop that continuously monitor and continuously improve the security posture of your environments. For example, let's make a concrete example. You could use Falco, and there are companies that do this, also very big companies like Shopify. They use Falco and define policies on Falco to detect a very strict set of policies they're interested in. And every time they find that somehow someone inside, someone outside stepped outside of those policies, they immediately have a team that creates up armor profiles for the containers and the kind of exploit that have been found. So they basically continuously, day by day, week by week, improve the security posture they have on their clusters and their fleet machine. I mean, their machine is their fleet is very big. It's like 300 servers. So what's runtime security? In the context I've just described, runtime security can be seen like the last line of defense. Let's try with a metaphor. She was Kelly. Look how beautiful she was, my little dog. I have locks on my door, and Wilson Allen. Think of these like compliance rules. But she alerted me when things were not going right, policy violations. When little bro was misbehaving with my mama, think of him like compromised insider. He still is very, very big compromised insider in my house. Or if there's something suspicious happening outside or nearby, anomalies, 0 days. So she detected runtime anomalies in my life at home. And she was, may she rest in peace, very serious about her job. I mean, look at the photo. She was very, very serious. So while prevention is about locking the doors, detection is about continuously monitoring the inside and the perimeter. The Falco unique way to do this is by, as said, tracing and detecting everything happening inside the box from the bottom, the kernel, up. Instead of using the usual top-down and sidecars approach like other security monitoring solutions and engines do nowadays. But how that's possible? Okay, we trace syscalls at their source, and then we need an engine that's able to create a mechanism to match what we found by tracing the syscalls to what we described with the policies. So we need basically a language and an engine that's able to, after a parser, an engine that's able to parse these towards a data set of signals and events coming from the kernel, plus signals and events coming from container runtimes, container metadata, Kubernetes audit logs, and so on. Okay, so maybe someone at this point could argue, why tracing the syscall? Why going so lower in the stack? Well, nowadays, the production environments are filled with, as I said, with so many pods, so many services, sidecars, containers, monitor tools. Things change every like 10 seconds. And I try to draw an abstraction diagram here on the right side. Don't criticize my designer skills. And this basically exemplifies today's typical production environments. It turns out that exactly this complexity, the one that I tried to abstract here, and the one that was some slides ago in the layered environments, is the exact reason we should go look under the hoods, if you think about. I mean, in the end, whatever program we run here, at whatever point in the stack, disregarding the language it's written with C#, whatever, C++, JavaScript, with Node.js or with some other JavaScript engine, who knows, whatever the language, whatever the syscall wrapper it uses, it can use Maslow, it can use glibc, it can use whatever. In the end, it will run, will end up making a lot of syscalls in the kernel. This because, at least for Linux, the system calls are the only, honestly not only, there are other little things, but are the principal mechanism to basically tell the machine to do things on the hardware, to do real things. And so whether the task regards networking, I/O, processes, so this does not matter at all. So thus, instead of looking at every layer here, putting a sidecar in every pod, in every system that our clients has, we just go under the hood, look under the hood, under the table, and we don't give a, sorry for the word, a fuck about what's happening above us. But to do this, a set of unique challenges arises, honestly. As said, syscalls are basically the API that abstracts the hardware for us. And they are very powerful mechanism, but not very much from a user space perspective. This because to bring a syscall, there's a separation between kernel space and user space. To bring a syscall happening to user space, for example, you have to do another syscall. Guess what you have to do if you want to know the time an event is happening? I mean, time in security, I think it's very important. Guess what? Another syscall. Except for the very braves playing with RDTSC, things like that, but that's another topic. That's a whole completely different story. Also, there are a lot of syscalls, and with every kernel release, they can change, and they do. They can gain new parameters, they can gain deprecations, new syscalls can be introduced, and things like that. So it can be really, really painful to keep Falco on track. But we can't do otherwise. I mean, otherwise the next talk title will be how simple it is to bypass Falco using new syscalls. And that's, by the way, the talk that I will give at KubeCon America in December. So please join me. Come look how to bypass Falco, my tool. So, furthermore, as we said, we need to combine this huge flow of kernel events we are obtaining, tracing syscalls, with data from other various tools that are very common in today's very complex setup. This because syscalls are the main interface towards the kernel and the hardware that it abstracts, but syscalls alone will not be enough, and we all know this. Will not be enough to create a software that deals with runtime security in real time. We want to connect these kernel events that we are grabbing from there with Kubernetes metadata or with data from the container runtime, with OD logs from other source of information. For example, if you use Falco to monitor your AWS something, AWS EKS cluster or whatever, you may want to combine the syscalls that are happening on the actual nodes with CloudTrail's audit logs. So to basically combine together more informations and gain more visibility, more actionable insights. But there's another issue here. Syscalls are very, very fast and performant. They happen at a rate that's completely different to the rate of Docker daemon, container API, things that we need to go look to gain these other actionable insights, which are, by the way, way slower of the syscalls. So there's another difficult point here was to basically create a way for Falco to asynchronously process every kind of information coming from Kubernetes, container metadata, or other sources in an asynchronous way and reconcile the data later with the syscalls information. So to know that at the end, the result was, and this, that you know the container ID, the container name, or the Kubernetes node name, the Kubernetes pod, where that syscalls for example, mounting etc hosts and dumping a lot of data inside, basically DOSing the nodes of your cluster was done. So that way you will be able to know exactly the container that was exploited, the container where the shell was spawned, and you can do some kind of forensics post-that analysis. Or in real time, if you attach the Falco alerts, because Falco can fire alerts via syslog, via gRPC, in various other ways, you can attach to that other tools to then do something automatically to, for example, eradicate that container, block that zone of the cluster, and things like that. Always in the logic that I told before to integrate the prevention and the detection phase. So this is in summary what the Falco drivers do, and we are going to deep dive a bit into this right now. Let me ask you a question. How to get syscall to user space and use them as one of the Falco inputs? I mean, the first option that came to our mind was to write a kernel module. Good luck with that, really, good luck. I will not have ever participated in it. I mean, doing a kernel module comes with a lot of downsides, both on the development side, named kernel panics, like 2 or 3 times a day, and the deployment one too. For example, imagine that you ship a new version of Falco and a new version of the kernel module input, and you need to contact people that's using Falco, maybe with the 300 machines fleet, and say, well, you just need to update your 300 DOS. Just write a script and update all the kernels there. And maybe you also need to tell them, you also need to compile the kernel module because you have that kernel release, blah, blah, blah. And so, I mean, it's not always suitable like as a solution. Also because in some environments like banks, kernel modules is not trust. Loading kernel modules is not allowed, usually. An alternative, so we need an alternative. And we thought, okay, what's an alternative now? We started investigating and we found, okay, there's this new cool kids technology called eBPF. Does anyone know what eBPF is here? No one, good, pretty good. I'm the only one knowing Linux here. I'm joking. eBPF is a new technology, really new, it's 2014. Honestly, it was created in 1992, but it was limited to packet tracing at that time. Then it was extended by Alexei in 2013, 2014, to basically create a technology to make us able to code the kernel without risking to panic it and without risking to expose holes or safety issues in the end. It's this because in the kernel has been created a virtual machine which puts lights on safety and security, a virtual machine that when receives the eBPF code, which is just a set of restricted C, statically analyzes it, and then just-in-time compiles it for performance reasons, and does some optimization. And while verifying it, the code that it receives before executing it, it verifies that, for example, there are not null pointer dereferences, that there are not unbounded loops, you cannot iterate, so it's not Turing complete, eBPF. And things like that. So to avoid, it happens, and it happened to me personally, that the eBPF virtual machine, which should be safe, and it's advertised to be extremely safe, in reality it is, can expose some bugs that makes it not that secure anymore. But that's another story. I mean, that's something that always happens in our field. So I should not spend another 20 minutes talking about the BPF, otherwise Giovanni will kill me, but maybe that's a topic for another talk. Okay. Last thing on eBPF is expose the same performances of the kernel module. There is just a bit of overhead, but in the 5%. So it's not, it's something very, and it's only usable on newer Linux kernel. I mean 4.4, but we suggest 4.14, 4.16. So if you have a fleet with of CentOS machines with 3.10 something kernels, you need to use kernel module. If you can't, there are other ways to input things to Falco we are working on. One is pdig, but it has been made for other kind of services. It has been made for things like managed Kubernetes services. For example, when you go on your cloud provider and you install things, a Kubernetes, that because you don't want to manage and handle Kubernetes installation, and I feel you, I mean in that case. But usually, for example, on AWS Fargate, you have no access at all to the host machine. So you cannot install in a BPF probe, neither a kernel module. No. And so we created pdig. Pdig basically is a ptrace-based producer that runs completely in user space. So you don't need a kernel there. It runs completely in user space and hooks the kernels up in the syscalls happening in the kernel with the ptrace and magic with the assembly trampolines. It's very hackish, very, very hackish. Slower, really slower than the other two methods, but I mean, if you have no other options, this way you could still install Falco with pdig and monitor your AWS Fargate clusters, because I mean, who knows what happens? Maybe you have compromised insiders, maybe would you trust your cloud providers to be able to to timely respond to any 0-day or an anomaly or CV that happens? I will not. So you need to monitor things. Okay, there's a diagram describing in a bit more detail how Falco works when using the kernel module as an input driver. As you can see, there's the separation I was talking about before between the kernel space and the user space. In the kernel space is where the kernel module lives. At the upper boundary of the user space, there's Falco on top of two other libraries, two other very important libraries that we do extensive use, libsysp and libscap. The kernel module attaches to the start of execution of every syscall that we track in the kernel, and also to the end of every syscall to grab the argument at start and post execution. With a mechanism we call fillers, then the kernel module basically augments, makes the arguments of the syscall human readable somehow. And finally, it also grabs contextual information from the operating system, and for example, from the proc file system on Linux. And finally, puts all this information in a ring buffer. Well, it actually does not put things in the ring buffer. It puts in the ring buffer only the memory pointer, so basically sharing that part of memory for performance reasons. But what's a ring buffer and why a ring buffer? That's a vital part of Falco. A ring buffer is an elegant circular data structure with a fixed size, 8 megabytes in case of Falco, acting as a first in, first out queue. It's very important because having millions of syscalls per second and having to process, parse them and match against a set of rules puts a really hard requirements on performances. And this was, for us, the only way for Falco to be effective, because we don't need to shuffle memory around when other events come in. With ring buffer, things just circle and you just get the last one. So you don't need to move memory to do copies and to do things like that that are very, very time-consuming. And when you use the kernel module, basically, the concrete implementation of the ring buffers, there's one for CPU, will be created like a dev devices. So you will, if you have 8 CPU, you will have dev Falco 0, dev Falco 1, dev Falco 7. And that will be the concrete implementation of this mechanism, communication mechanism between the kernel and user space that we use. Once we have data in user space, which are grabbed through libscap, libsysp enters the games and does that thing of reconciling these syscalls with the other contextual information about the context where they happened. For example, grabbing the container ID, the container name, the container image name. Maybe you have, maybe someone created an executable in a container, and you want to know which image has been, which image has lost its immutability, and things like that. And then everything comes to Falco, where there's the engine for the language and the policy matching. Then I said companies that want to use Falco write to you, hey, Falco seems very, very, very cool, but we cannot allow to insert a kernel module because blah, blah, blah. I mean, they have reasons to disallow the insertion of a kernel module. And after a bit of time, we say them, well, we got you, no worries. You can have the same exactly functionality using this new cool kid technology, BPF, since we built a BPF probe too. In this case, as diagram shows, there's no ring buffer involved because the BPF virtual machine does not allow you to move memory between the kernel and the user space. And for reasons, I mean, its purpose to be very safe would have been complete garbage if they would have allowed that. Anyway, luckily, eBPF has this feature, very, very cool, called maps. As you can see in the diagram here, basically the maps are the vital part of the Falco architecture in this case. In this use case, here we have a library, libscap, that's responsible basically to get the health of the compiled eBPF source code, parse it, parse the eBPF map sections that we found it, parse the raw trace point that we put on syscalls, the normal trace points that we put on syscalls, the other things that we do, uprobes and things like that to grab other informations, and mount everything of this in the kernel, in the BPF virtual machine, and so let the BPF probe of Falco run. When this is running, libscap also receives from the map that he created data through the BPF maps. And this data will flow to libsysp that again does the same game of before, so reconciling this data with Kubernetes data, container metadata, container runtime data. It took a while for us to reach this point, but on the top level of the diagrams that we've seen right now, there was Falco with the icon of Falco, and what remains of Falco is just very simple, continuous loop that reads those events by calling the next method of a libsysp inspector instance, and outputs alert about security threats you declared with Falco rules when its engine finds a match. I mean, I removed a bit of code here, but this is what basically all Falco does. It's very, very simple, and all the magic is clearly in the eBPF probe or in the kernel module probe. Here there's a bit of magic with the engine, with the language, but nothing really cool as the other two things. Notice also that the Falco rules language has, as we will see very soon, operators and filters provided by libsysp, which is part of Falco implementing for the filtering mechanism of those events. So maybe asking yourself now, maybe I bored you so much, okay, Leo, but how do we define policies? Go straight to the point. How do we describe what is a security threat for us? The answer is pretty straightforward with the Falco rules language. The Falco rules language is also very simple. It's a YAML subset, and this makes it very, very easy to learn and very hard to indent correctly, but that's YAML fault, not my fault, sorry. And, don't laugh because I laugh always. Sorry. And like other policy languages, where basically, I don't know if you ever tried to write a link policy, ARM, or things like that. YAML is very simple. The only defect is the indenting of YAML, but it's very, very simple to learn. You can write conditions, you can group conditions into macros to later reuse them, you can write lists to have more easier comparisons in conditions, you can give names to rules, you can even customize the output that a rule when files will give you, customizing the output field that you want. Maybe you don't want the container ID, you just want the container name, you can change it. It's very, very simple. And very, very soon we are working on also on another thing that's exception for rules, because in some environments maybe you don't want fire alerts for something that you know that can be an issue, but it's an issue that you can allow. And so we are working also on exceptions for rules. What else? We have a very, very big default rule set. I don't remember how many rules are, but it's a huge file. There are like 5 YAML files, one for Linux security, another for applications like databases, things like that. You can find them over in the rules directory of the Falco repository. Go there, grab them, try them. But other things that, there are a lot of rules. We will need a week to look at every rule that we provide, but 2 rules, 2 macros, 2 things that it's worth mentioning, in my opinion, right now, is the spawned macro. That's a macro that you can use to briefly, in a pretty straightforward way, create rules to detect when someone spawned a shell in your containers, in your environments, whatever. Or the cloud metadata from container. Basically, a very common pattern in cloud native contexts is to abuse the container metadata server to grab some credentials and secrets, and that link put a rule that's used by Falco users to detect when someone is using this mechanism, this approach to exfiltrate credentials, seek tokens from the cluster and so on. Let's now see this. This is another example of another abnormal activity detected by Falco. I'm referring to a very, very common remote code execution use case called container drift. This means that in some way, someone changed things in the container image, changing the immutability of the container image, as I was saying before. A subset of such changes are executables created in a container at runtime. Detecting such behavior can really help flag critical security issues related to remote code execution. So, as you can see in the slide here, we define a rule to fire an alert when a new file is created in a container with execution permissions, and we use the isOpenExec filter of libsysp that Falco provides us. But I recorded a demo on ASCII Cinema. I don't know if I can click here and try to. Let me try. If I found the mouse, I don't know where. Okay. Nope. Come here. Okay, let's take a look at the demo. Okay, for the sake of simplicity, I already created the rule set containing only this rule to detect container drift. As you can see, the same that I put in the slide, there are some macros to basically exclude Docker and runc container runtime from throwing this alert, because we know that we are using Docker. And basically, we are using this OpenExec, and event type, the event of syscall is open@, create. We are in a container, and this action was not done by runc or by Docker. So basically, we now start Falco with -r, giving this YAML to Falco. Falco starts, and now we will try to run a container, maybe an Alpine, an Ubuntu, I don't remember what I ran here. and we try to write in the container with the toolchain of the container that exists in the container. This is a reason why you should never put toolchains in containers in production. Thank you very much. And basically, we will try to now create a malicious little C file, compile it, and execute it. And we will see if Falco is able to detect it at runtime or not. I don't remember if, okay. Basically, we are creating here, we are doing a syscall, a create syscall with open on a file called blah blah. We compile it, and we execute, and Falco detects that basically someone in the container created, executed a command add with a file, creating a file blah blah that's a new executable, and we are done. So, it seems to work, Falco, I don't know. Now, I don't know how to come back to Falco here, if I found the mouse. Is on the right? Yes. Okay. But, okay. Let's move on. Can I come back to this one? Okay. Let's move on. So, bad things can happen, right? For example, recently on Kubernetes, a CV has been found, and it affected a lot of Kubernetes versions. I mean, we all agree that detecting exploitation attempts of this vulnerability is critical, right? This CV was a bit critical because it was a server-side request forgery in the kube controller manager, basically allowing certain users to leak up to 500 bytes of arbitrary information from unprotected endpoint within the master's host network, so such as loopback services. This can be caused by an attacker with permission to create a pod or a storage class with certain volume types to cause the kube control manager to execute some get or post requests from the master's host network, which means you can grab credentials and things like that. The good news is that with Falco and also Falco YAML language that guy was loving so much, it's very easy to write rules to detect this and at least detect this. Then the mitigation can be done with other tools. But to detect this, basically, you have to write a condition like this. We are in a Kubernetes event. We are in a pod, in a creation phase that's going with SASs on. And there's one of the affected volume in the pod. And there's the macro affected volumes in pod that basically lists Scale.io, Kubernetes, GlassRFS that were the volume providers affected. So basically this way, you detected half of that CV. And in the other way, the other part of the CV was about not pod, but storage class. So again, we are writing a condition that says, okay, is this a key FT, a Kubernetes event, and a storage class is being created successfully with one of the affected storage classes. That's just a list and a macro that uses the in operator, because Falco has all these operators, match, in, contains, things like that. It's a language. And so this way, you can, like in zero time, if you have Falco on your Kubernetes cluster, detect if someone is using that CV on your cluster. We should probably move forward. I don't know how much time I have, but and probably I'm hungry, so we should go eat something now. But nevertheless, for the very braves interested in learning more about Falco, the importance of runtime detection, even in environments like Kubernetes and containers, that should theoretically provide better isolation. I mean, at least this is how they advertise containers, Kubernetes, isolation, theoretically. But in reality, there's a lot of fun out there. I put here 2 pointers that I consider worth to take a look at. They are 2 very, very recent CVs that have been discovered that use a.k.a. against Kubernetes cluster. The one on the left on July, that one is like 10 days ago. The one on the right is, the one on the left is about exploiting a bug in the Kubernetes kubelet that was basically not considering in a completely correct way the pods mounting etc-os. So basically letting the attacker mounting etc-os in some cases and putting a lot of data in, like a lot of data, I mean 1 megabyte, 2 megabytes in the etc-os file, basically DOSing your nodes with just that. So basically create a pod that mounts etc-os and puts a lot of data inside etc-os, the first things that it does when it runs. It will bring your nodes, it will DOS your nodes, like denial of service. So it's a medium severity one. And I put the link, there's a link on how to detect it with Falco and mitigate it with AppArmor profiles as soon as you detect it. On the right side of this slide, there is the other CV, the very recent one, that was discovered in reality, was used on Kubernetes, but has been discovered in the packet socket facility of the Linux kernel. It affects all the Linux kernel greater than 4.6, so a lot of versions since we are today to 5.8, 5.9. And basically it affects all major distributions of Linux. It can be used to gain root access from unprivileged local process, so also from containers and pods. This is why they use it on Kubernetes. It allows a bad actor to trigger memory corruption that can be used and exploited to hijack data, resources, and in the most severe cases take complete control of your system, of your machines. So I will consider to go read this if you have like 10 minutes of spare time, because it's very, very funny, let's say this way. As promised, at the end, here in the slide, I put a bit of resources for those interested maybe in learning more about BPF, this technology that we use to trace everything happening in the Linux kernel. I did a podcast for Google about BPF. You can find it at the first link. Or you can read the book from my colleague about BPF, Lorenzo Fontana. Or if you're just interested in looking at the ring buffer implementation or the fillers to make the syscalls data human readable, just go there. For people that love YAML, they can click the last link, Falco default rule set, so they can look at like 10,000 lines of YAML. So that's it. If you have any questions, please feel free to throw questions at me. Otherwise, you can find me on the Kubernetes Slack, on the Falco Slack, on the CNCF Slack. I'm Leodido everywhere. Feel free to contact me, ping me over Twitter, follow me, ask me questions. Thanks to everyone.
Thanks, Mel.